This is video 5 for the rotation unit. In this one, we're going to start talking about energy, specifically rotational kinetic energy. Now, we only have to worry about kinetic energy because potential energy, well, it doesn't really care if it's in a line or rotationally. It's something being held at a position. So we just need to worry about rotational kinetic energy. So spinning objects will have kinetic energy. They are moving. But we have to use a different method to calculate that rotational energy. Let's begin with translational kinetic energy. By now, this should be a very familiar model. Okay, now let's add in the bridge. V equals R times omega. So we can do a little bit of algebra here. And I want you to pay close attention to the mr squared part of this. That would have units of kilogram meter squared, which is the unit for moment of inertia. So, our model then for rotational kinetic energy is 1/2 moment of inertia times rotational speed squared. It's a pretty simple model, very, very similar to translational. Now let's use it. Let's say we have a solid disk and a ring. And both this disk and ring are manufactured to have the same mass and radius. We're going to put both of them on the same length ramp, elevated to the same angle. And we want to find out which object will reach the bottom of the ramp in the shortest amount of time. So this just screams out conservation of energy. So let's take a look at some of the things we know. We got our delta y. We have our angle. Got the length of the ramp. So there's a lot of stuff that we already know. We know the initial velocity will be 0. And if we really want to find out who's going to win this race, we probably ought to find out the final velocity. So conservation of energy tells us that as long as there are no non-conservative forces, all the energy in the system will remain constant. The mechanical energy will remain constant. So what that means is all of the starting potential energy must equal all of the final kinetic energy. In this case, we're starting off with gravitational potential energy because there's only one force that's acting on this. It's a gravitational force, and that is conservative. At the end of the ramp, this thing will be rotating, so it will have rotational kinetic energy. But it's also moving translationally. So it's going to have both rotational and translational kinetic energy. In fact, these two always come as a pair. Whenever you have rotational kinetic energy, as a general rule, you will also have translational kinetic energy. So, just using our simple model, we're close to the surface of the Earth. Started going into spring constant there. So there we have it. We got this model right here. mg delta y equals 1/2 I omega squared plus 1/2 mv squared. Now I, the moment of inertia, is going to be different for the disk and the ring. So we have to do them separately. Let's start off with the disk. So the moment of inertia for a disk is 1/2 mr squared. where r is the radius of the disk. The next thing, v equals r times omega, so omega would equal v divided by r. We can get rid of that omega. I do that because I want this in terms of v. So I need to get rid of that omega. Now when we do a little bit of algebra, notice that the mass cancels out. And notice that this r squared, and I'm going to have v squared over r squared, so the r squareds cancel out. So then the speed of the disk at the bottom of the ramp will be the square root of 4/3 g times delta y. And if you know the length of the ramp and if you know the angle, you can use a little bit of trigonometry to figure out what that delta y is. So that's not too bad. All right, now let's figure out the ring. The moment of inertia for a ring is just mr squared. Once again, we're going to plug in v over r for our omega. Again, I want you to notice that mass cancels. The r squareds cancel. One half plus one half is just 1. So it's just going to be g delta y. So which one was faster? Hopefully you can see that it's going to be the disk. 4/3 is greater than 1. So comparing those two, 4/3 g delta y is bigger than just g delta y. So the disk will be traveling faster at the bottom of the ramp. If you wanted to figure out how much time it takes, go to kinematics. So looking at this model right here, our universal model of motion, the initial position is 0, the initial velocity is 0, x would be length of the ramp, so t would be twice the length of the ramp divided by the acceleration of the object. Okay, you may be wondering, okay, where will I get the acceleration? We can use the v squared equals v naught squared plus 2a delta x. And in this one, again, the initial velocity is 0. Delta x would be, again, the length of the ramp. So acceleration would be v squared over 2l. So I can plug that in. So I see that my time would be that. So when I do a little bit more math with this, I can flip these over So the time it takes would equal 2L over V, and then I could just plug in my two numbers I got for the velocities for the disk and for the ring. All right, that hopefully that also is a good reminder for conservation of energy. We'll finish that video here and talk about momentum next.